Recent findings from China's Chang'e-5 mission have revealed groundbreaking insights into the moon's volcanic history and the behavior of lunar dust under electric fields. These discoveries show that the moon was volcanically active much more recently than previously thought, and the unique properties of lunar dust could revolutionize how we approach future lunar missions and habitats. In this video, we'll explore these exciting findings, explain why they're so important, and look at how they could reshape the future of lunar exploration. The Chang'e-5 mission brought back samples that were subjected to an external electric field to study their charging properties and behavior. You might think, it's just dust, what's the big deal? Well, lunar dust is far from ordinary. It's jagged, abrasive, and clings to everything, posing serious challenges for astronauts and equipment. Researchers exposed these dust particles to an electric field under high vacuum conditions, mimicking the lunar environment. They observed that the particles, which range from about 27.7 to 139 micrometers, tend to gain negative charges much more easily than they would on Earth. This change affects how the dust moves and sticks to surfaces. The experiments showed that lunar particles behave quite differently in space than under Earth's atmospheric conditions. When these particles gain charge, they can become airborne and cling to sensitive instruments, spacesuits, and solar panels, potentially impairing mission-critical systems. So, what's the big deal? Let's look at the evidence. The study observed that when charged particles collide with surfaces, they can cause abrasion, coating degradation, and other forms of damage. This isn't just theory. Materials like MLI and aramid cloth used to protect spacecraft from extreme temperatures and radiation showed visible damage when exposed to charged lunar particles. Over time, this kind of damage could compromise the integrity of a spacecraft or habitat, leading to mission failure. As we consider the possibility of establishing lunar habitats, protecting those environments becomes critical. The moon's lack of atmosphere means dust can be lofted into the air by the slightest disturbance, sticking to surfaces and even entering habitats through airlocks. This underlines the need for robust shielding solutions, including advanced materials that can withstand constant exposure to charged particles. Recent findings also reveal that the moon's volcanic activity may have persisted much longer than previously believed. Volcanic glass beads found in the samples suggest that the moon was volcanically active as recently as 123 million years ago, implying that heat-generating elements like thorium and rare earth elements are still present in the lunar mantle. This volcanic activity suggests that the moon's interior remained warmer than expected, challenging our understanding of its thermal evolution and extending its volcanic history by 800 to 900 million years, up to about 2 billion years ago. This indicates that heat sources within the mantle could still generate localized thermal energy, potentially allowing for geothermal power on the moon, which is an energy source that could be harnessed to support future lunar bases and reduce dependence on Earth-supplied power, making sustainable lunar exploration a more feasible reality. Manipulating lunar regolith isn't just about managing dust. It's about transforming a potential nuisance into a valuable resource. One of the most promising applications is in situ resource utilization, ISRU, where lunar dust and regolith are processed and repurposed for various needs. For instance, dust particles can be raw materials for constructing habitats, landing pads, and protective barriers. Techniques like sintering, which fuses dust particles into solid structures using heat, could enable the building of infrastructure directly on the moon, reducing the need to transport materials from Earth. The discovery of new minerals, such as changesite Y in Chang'e-5 samples, highlights the moon's dynamic past, revealing its impact history shaped by volcanic activity and asteroid impacts. Studying these minerals provides valuable insights into the moon's geological evolution and helps us design better dust management and shielding technologies tailored to withstand the harsh lunar environment. Beyond historical insights, manipulating the charges of lunar dust particles could enable the direct separation and collection of valuable minerals on the moon's surface. This revolutionary approach to mining could allow us to extract critical elements like oxygen, silicon, and metals essential for life support, manufacturing, and power generation. These minerals also present opportunities in advanced material sciences, such as developing high-strength ceramics, heat-resistant materials, and solar cells, specifically designed for lunar conditions. Technological innovations in dust mitigation, such as electrostatic dust shields and magnetic dust removal systems, are crucial in enhancing equipment longevity and operational efficiency on the moon. Electrostatic shields use electric fields to repel dust from surfaces, protecting solar panels, habitats, and spacesuits from dust accumulation. Similarly, magnetic dust removal systems attract and capture charged particles, helping maintain critical equipment during surface operations. ISRU extends beyond dust. The broader lunar resource economy includes mining elements like helium-3, which has the potential to be a clean energy source for nuclear fusion, powering future lunar and space missions. The extraction of water ice from permanently shadowed craters near the lunar poles is another crucial aspect, providing water for life support, rocket fuel production, and sustaining a long-term human presence on the moon. The insights gained from Chang'e-5 are already shaping future missions, such as NASA's Artemis program and the Lunar Gateway. By informing strategies for dust management, habitat construction, and resource extraction, these findings align with the broader goals of establishing a sustainable human presence on the moon. The moon also serves as a testing ground for Mars, offering a platform to refine technologies for dust management, resource extraction, and habitat construction that will eventually be deployed on the Red Planet. Thank you for watching. If you enjoyed this deep dive into the latest discoveries from Chang'e-5 and their game-changing impact on lunar exploration, be sure to like, subscribe, and hit the notification bell so you don't miss our next exciting update. Let us know in the comments what you're most excited about regarding our future on the moon. Until next time, keep looking up.